Okay, moving into the second section of Chapter 8, we are answering the question, how are rates of growth compared between functions? And once again, just like 8.1 where we talked about L'Hopital's rule, we're kind of getting back to this idea of limits a little bit, so it's going to seem a little familiar. We're kind of coming full circle. So actually an exercise we did in Chapter 2. I asked you to order the following functions here from fastest growing down to slowest growing, and I kind of put that in quotes because we didn't really define what that meant. We were kind of working off of our intuition, and I gave you that list of 6 functions, and I said use your calculators, and you went through ordering them from what you pictured being the fastest growing to the slowest growing, and it really had to do with like the rates of change, but we really did it graphically. So what you did was you, again, experimented with your calculator, with table, looking at that, and we came up with a list. So maybe you want to pause it, kind of think about that again, what the order was, but I am going to go over it right now. So what we had determined was that an exponential will always grow the fastest. So that was your 2 to the x. So anything that's got a variable in the exponent, that change is going to get really magnified as that x gets really large. The next thing would be the polynomial, so that would be the x squared. The next thing would be the linear growth, so there's your y equals x. The next would be the square root of x. So think about that. That's actually the inverse of x squared. So you're going to see sort of a mirror image here. And then the slowest of the functions with variables in them would be natural log of x, which is really, the inverse of an exponential, specifically e to the x. And then down at the bottom, y equals 2. If you think about that, that's really not even growing. All those other ones, as x gets bigger, the y value gets bigger, y equals 2 stays the same, so it's not really growing. So we worked off intuition, but the question might be, how do we really know? So here's what we do. We sort of define it this way. So if we want to look at a function growing faster or growing slower, what we do is we can compare them as a quotient. And so what you'll see here is we are looking at taking the limit as x approaches infinity of one of the functions over top the other function. Frankly, it doesn't matter. You kind of read this definition and it works back and forth. So the function f would grow faster if when you put f on the top of the fraction and g on the bottom, if the limit is infinity. Now, if you happen to have flipped it and you put f on the bottom and you get 0, well, that still means f is growing faster, which means g is growing slower than f. Now, the second part of this definition is a little bit disconcerting for some. So we're talking about growing the same rate. So if you take that limit, and if you don't get infinity or 0, if you actually get a number, and that number is not 0, so that's what that represents there, that L, an answer to the limit problem not equal to 0, then we say those functions grow at the same rate. Now you'll see some problems where maybe you'll be questioning that, because if I'm dividing those two functions and I get an answer of 5, let's say, doesn't that mean that the one's growing 5 times as fast as the other one? Not exactly. It means that the the y values are 5 times as tall, but when we talk about growth rate, we're really talking about like a variable change in the rate. So getting a constant answer for our definition, it doesn't mean that the one function's not taller than the other function, but in terms of their growth rates as a variable change, if you get a numerical answer with this quotient, they are considered to grow at the same rate. That bottom idea there, transitivity, hopefully is a really easy one to grasp. If a function f grows at the same rate as g, and g grows at the same rate as h, then f grows the same rate as h. That goes all the way back to your Algebra 1 transitivity idea. You can also use that as an inequality comparison too. If one function grows faster than another, and that one grows faster, etc., etc. Okay, well, it's kind of short. Let's take a look at a couple problems, and we'll see what we come up with here. So first one, which grows faster, e to the x or x squared? So this is something that maybe we would look at limit questions with this before, but a lot of times we were working off of like just memory, intuition, but now we have a little bit of information to back it up. So for the first one, we would take the limit as x approaches infinity, and you take your pick. It doesn't matter which one you put on top or bottom, you just have to interpret the result correctly. So if we do e to the x over x squared, we'll find that limit. Now, in the past, we would kind of go with this idea, well, exponentials grow faster, but now we have something to help us out, and it shouldn't be a surprise that this comes after L'Hopital's rule, because if we look, when we plug infinity in, we've got an infinity over infinity case. So that means we can take the derivative of the top and of the bottom, not of the entire function. So the derivative of e to the x is e to the x. The derivative of x squared is 2 to the x. Still infinity over infinity. Take the derivative again. Now we've got e to the x over 2. Well, now it's pretty clear. The top is going to infinity. The bottom's always 2. This thing is going to infinity. Now, if it's going to infinity, that means the top is growing faster than the bottom. If it goes to 0, the bottom's growing faster than the top. Here, the top's growing faster, so we would say e to the x grows faster. Second one. After I clean up the screen here. So the second one, which grows faster, natural log x or 3x squared? Well, let's take the limit as x approaches infinity. I'll just go in the order they have it there. They have natural log x first. They being me, I guess, over 3x squared. And well, natural log x, it doesn't grow too fast, but it will keep getting bigger as x gets bigger. So this is an infinity over infinity case. I will apply L'Hopital's rule. So the top, the derivative of ln x is 1 over x. The derivative of the bottom is 6x. Well, now it's not infinity over infinity anymore, because if I plug infinity to the top, 1 over infinity is 0. It's 0 over infinity, but I can do some algebra simplification. So 1 over x divided by 6x, that's like multiplying by 1 over 6x. This thing simplifies to 1 over 6x squared. This one, hopefully again getting a little clearer, even though infinity is involved. We're squaring infinity, taking to times 6, 1 over that thing's going to 0. And so if it's going to 0, that means the bottom's growing faster. So 3x squared grows faster. And, whoops. You could also answer by saying natural log x grows slower, and that would be just fine. And one more we can peek at would be this one down here. And this is to stress really that there's some cases, those want to erase over there. There's some cases where L'Hopital's rule either isn't necessary or doesn't apply, or can sometimes make the problem actually even a little bit more difficult. So this one right here is a good case of that. I've been tripped up on problems like this before. It says, which grows faster, x squared or the square root of 3x to the fourth?
Please call 8100.
Anyway, x squared or the square root of 3x to the fourth minus 2x plus 7. I would probably have the tendency to put the more complicated one on top. I think that can sometimes work out just a little cleaner. So we'll put square root 3x to the fourth minus 2x plus 7 over x squared. Now, you look at it, it's an infinity over infinity, so you might be tempted to say, hey, this is a great chance to use L'Hopital's rule. But you will see that it will get messy really fast. When you plug that infinity in, when you take the derivative of the top, you've got a big mess to the 1/2 power. You're going to bring down the half, leave that stuff here, make it a negative 1/2, take the derivative of what's inside. Sometimes that works, but sometimes if you can just rewrite the function, that will work. And so, here's a way to rewrite this. That denominator is an x squared. I can bring it under that square root if I made it an x to the fourth. because the square root of x to the fourth is x squared. So I can bring it in so everything's under the square root. Now there's a couple of ways of looking at that then. One of our limit rules is if you have the limit of a root of a whole function, you can just take the limit of that function and take the square root. Like operations are sort of, this is not the right word, but factorable out of limits. So that's one way of looking at it. If that's the case, we could sort of get rid of the root, maybe apply L'Hopital's rule, bring the root back in, and we'd be in business. Another way for this one that you'll commonly see it done though is just term by term dividing by x to the fourth, since there's a single x to the fourth. So you'd have the square root of, well, 3x to the fourth over x to the fourth is 3, minus, then it would be 2 over x cubed in the middle, and then plus 7 over x to the fourth. Well now, if x is approaching infinity, the middle one goes to 0, the last one goes to 0, you're left with a square root of 3, and that's your answer. Square root of 3. So didn't look at any transitivity problems here. We'll look at those in class if necessary. And one thing I want to point out, we are going to clean this section up a little bit and make it go a little faster. If you look at the bottom here, we're not going to do any of the big O, little o notation. There's also a little section about like search engines and binary searches. And how that works with making the, the fastest algorithm. We're not going to look at any problems with that. It probably would be an interesting little read. But what we'll do, and I'll mention this in class, is we'll omit 30, 32, and 34 from the homework. So we'll be ready to summarize tomorrow and go over this work.